Welcome to the presentations for the finalists from the 2017 Hackathon. This is our third Hackathon ESPN has sponsored, and this year we were joined by Ticketmaster to sponsor the Hackathon. So we will have, the winners will be announced at the Alpha Awards this afternoon, so you can come and check out, see who wins. The winner, thanks to Ticketmaster, will get a trip out to Ticketmaster offices to present their work to the Ticketmaster data science team. So big new prize for them. And so I'm excited to see what we've got. So we started with over 180 applicants for this hackathon this year, which was a record for us. We whittled that down to 47 people we accepted to actually come on Thursday and spend 6 hours working on SportView data. And then out of that, we selected 3 students and 3 open division finalists to come and present today. They were given 90 seconds on Thursday to present. They have 5 minutes today, so and with a little less pressure, so they can dive a little bit more into what they were able to do on Thursday. What they were supposed to do, what the task was this year, was to measure the immeasurable. Because in sports analytics, what we often run into is, well, stats are great and everything, that's really nice, but you can't measure heart. You can't measure grit. You can't measure team chemistry. Well, sure, right now we can't. But maybe with this new data and some creative minds, we can get closer to those things, and we can take some of those things that are intangible and make them a little more tangible and understand their impact on the game. So that was the goal for our hackers, and so I'd like to bring, we'll start with our students today, and one by one they'll talk to you about what they did and what they were able to accomplish. So we'd like to start with Melanie Lewis. If you can come on up and talk to us about your project, please.
Okay, so my name is Melanie Lewis. I'm from the University of Oklahoma, and I am going to give you a brief introduction to some theory from the field of industrial organizational psychology. So the motivation behind the good soldier syndrome was to come up with a way to describe and understand the type of people at work who really go above and beyond what is required of them. And in so doing, they often behave in ways that sacrifice their own personal performance to benefit the performance of others or to benefit the organization as a whole. So these behaviors are referred to as organizational citizenship behaviors, and they're defined as discretionary behavior or extra role behavior that isn't easily incentivized. So what kind of people are likely to perform these behaviors? Research has shown that they tend to be more conscientious people who are satisfied with their job and committed to the organization. And they also tend to perceive their leaders as being more supportive, and they have positive leader-member exchange. And as a result of organizational citizenship behaviors, in the aggregate, what we see is there's reduced employee turnover, and the organization is more productive and more efficient. So the real question is, how do you measure something like the good soldier syndrome when it's not something you can really observe? So much like someone's personality, you can't look at someone and see what their personality is. Instead, you infer what their personality is based on how they behave and how they interact with other people. So in this same sense, to measure the good soldier syndrome, we would identify what type of actions that a person who has this trait is likely to do in a given context. So in the context of basketball, these need to be behaviors that aren't on your traditional box score. You can't get a triple-double by doing these things. So the behaviors I chose are secondary assist, rebounds deferred, passing the ball, taking a charge, and putting in some effort on defense. Now, method-wise, if you want to measure something that you can't observe, we use latent variable modeling, which is confirmatory factor analysis. So what we have is some underlying trait that we're attempting to estimate based on observed behaviors that really aren't perfect representations of this trait. So some variance in all of these 5 behaviors is going to be explained by something totally unrelated to what we're trying to measure. So the goal is to estimate how much of that variance is explained by this single trait. So when I fit this model, what we see is that someone who is a good soldier, so to speak, takes more charges, plays tighter defense, defers more rebounds, has more secondary assists, and passes the ball a lot more. Now, this all makes sense, but with psychological measurement, we also want to make sure that what we're measuring is reliable and that the inferences we're making using these traits are valid. So reliability is something that you can get using internal consistency across these 5 variables, and you want it to be around 0.7, and it's close, but it's not quite there. As far as construct validity, this single factor model does fit quite well, so one underlying trait explains the covariance in these behaviors. And what's probably the most important for a team is, does the good soldier syndrome predict team outcomes? So using just simple regression to predict individual player plus minus, what you see is it doesn't really predict that very well. It only explains about 5% of variance in plus minus. As far as the overall team record for the whole season, it's not a significant relationship, though it does explain about 22% of variance in the team's records. But what is great about it is that it explains almost 75% of variance in team points scored in a game. So having selfless players really does benefit how much a team can score. And with that, I end with a quote, so thank you.
All right, our next student, Evan Green.
Hi, I'm Evan Green, and I looked at vision for passers in the NBA using some of this tracking data. And what I mean by vision is that's kind of a nebulous term. So I wanted to explore the extent to which passers are flexible, unpredictable, and creative in their passes. The reason I chose these kind of criteria was that I thought this would help somebody who's flexible, unpredictable, and creative would be harder to guard because you wouldn't know where the ball is going. So I created 2 metrics. One I called entropy. This is about whom a player is passing to and the unpredictability in that. And then clustering, this is where a player passes from, and this is about the unpredictability in where they're passing the ball. First, entropy. So entropy is the ability for a player to spread the ball around, pass to all his teammates, and not just lock in on one player. So here we can see the relative distributions for Marvin Williams and James Harden and who they're passing to. You can see Marvin Williams is almost about 65% of the time passing to Kemba Walker. And this makes his entropy pretty low, just 1.9. And this makes sense because he's somebody who, if you're guarding him on offense or on defense, you always kind of know where the ball's going. Where James Harden, you see his distribution much more spread out, and his entropy is much higher, meaning that he is harder to guard, more unpredictable, and more creative. Also wanted to look at clustering. So this is the extent to which the points are clustered compared to a random array of points. And this is like a single number that kind of explains what you're seeing in the difference of these 2 distributions. And the way I came up with, the way I measured this metric was I took the amount of passes that somebody took, created hundreds of random distributions drawn uniformly from the court, and looked at how clustered those were compared to how clustered the actual distribution was, because you have to account for the number of passes people are taking, since points are closer when there's more of them. So here you can see Spencer Hawes on your left. He's almost always passing from, top of the key, kind of around the 3-point line. That makes it easier for somebody who's guarding him, if he's not in that area, to know that he's probably not going to be passing. And then where Patrick Beverly, he's kind of passing from all over the court and therefore has a lower clustering. And I wanted to look at the relationship between these two variables because to, one, make sure that they're measuring kind of similar things since they're both measuring vision, and then also see who's the best at it. So we can see that, so down and to the right is better, that's less clustering and more entropy, more randomness, better vision in your passing. We can see that there's like the negative correlation, which makes sense, so that players that have higher entropy have less clustering, which is what we would expect. And then we also can see from the positions of the players that it's what we expect as well. So in the top left, we have, DeMarcus Cousins, Spencer Hawes, Dwight Howard, these are the bigs. And then in the bottom right, it's guards, point guards, and then the only non-kind of guard is LeBron James, who we all know is a great passer. Now, of course, with passing, we wanted to make sure that it actually helps predict, some outcome that we can see. And so I wanted to look at if entropy and clustering can predict assists. And I used adjusted assists here because an adjusted assists include both normal assists and secondary assists and free throw assists because all those contribute to points. And we can see that if you do entropy and 1 over clustering to make it so that it's a positive coefficient, we can see that they explain assists pretty well, even in this fairly limited data set with a statistically significant coefficient and a reasonable fit. Thank you.
Student Benedict Brady.
Hi, everybody. I'm Benedict Brady from Harvard University, and I looked at quantifying the psychological effects of a made shot. So when you make a shot, it kind of impacts the way that you think about maybe the next possession, maybe the next couple of possessions. We see basketball as a streaky game, and so the question is whether or not we can see this in player behavior. And very specifically, I'm looking at if this impacts defensive aggressiveness. So we've seen players get motivated by a successful shot. They play higher intensity defense. Maybe they're looking for a steal, maybe they're looking for a block, and so they get up really close on the next possession to try and build momentum for their team. So what method can we look at to identify whether or not players are playing more aggressively? So we have location and play-by-play data, so we can combine them and identify all of the shot attempts, and then we can look at the player who has made or missed the previous shot, and now they're playing defense, and we can look at how involved they are in the play. And so our metric for how involved they are in the play is their proximity to the nearest person on the opposing offense. And so we iterate through all of the location data every 4 milliseconds, and we identify the closest player on the opposing offense, and we take that distance. And then we should look to see whether or not a miss or a make on the previous possession is a significant predictor of their proximity. And so what we find is that it is a significant predictor, and it is negative, which means that players, on average, play about a foot closer to the opposing team after they have made a shot. But we can look at this over time. So here we have a graph of the time after the shot has occurred versus the proximity that the defender is taking. And what we notice is something pretty interesting, which is that if you look at the first 3 seconds after the shot, we can see that you're actually farther away after a make than you are after a miss. And this is because players have to take the ball out from the baseline, and the defense has time to get back, and this creates an artificially large gap. But that after the first 3 seconds, once the team has taken the ball down a little bit, this corrects, and now the players who have missed their previous shot lag off a little bit more. And, of course, we can look at this with a regression again. So we can break up the shot clock into 21 to 24 seconds and 5 to 21 seconds. And as we can see here, 21 to 24 seconds, there's not really any significance. If anything, it's the other direction. But from 5 to 21 seconds, we can see that it is a negative predictor again. So what are the conclusions of this? Obviously, there can be confounding factors here. We only have 5 games of data. Potentially, there may be a selection bias issue where players with higher field goal percentage play tighter defense, but this is probably a basketball inefficiency because after the play is set, there should be maybe an optimal way to play defense that it has nothing to do with whether or not you as a person have made or missed the last shot. If anything, maybe players should play more aggressive after a miss because they've missed an opportunity and now the gap between the two teams is wider. So one final thing I want to talk about a little bit is related work that I did on this. So this was the article that I wrote in January that was an inspiration for this a little bit. And so there are more things that you can look at after a player's made a shot. And specifically, I looked at whether or not players take the next shot more frequently after they've made a shot versus after they've missed a shot. So basically, like whether or not players believe in the hot hand. What I found is that players use 22% of their team's possessions to shoot after they've made a shot versus after they missed a shot. And so it seems that a made shot may have like a wider array of impact on behavior than people previously thought. And there are pretty reasonable ways to quantify this. Thank you.
All right, so we've cleared through our student division. We're now going to move into our open division where more experienced professionals competed. We have our first open division finalist is Konstantinos Pelakrinis. I hope I got that right.
Hello, my name is Kostas Pelakrinis. I'm from University of Pittsburgh, and I used complex systems to measure team chemistry. So team chemistry is one of these intangibles that you can actually not even define through words. So the way I used in order to define team chemistry is based on the expected results that you would have if a team exhibited good team chemistry. And these, the two things I used is that you expect the team to have good ball movement and good connectivity between its players. However, these two are still kind of vague, and the question becomes how do you measure actually ball movement? So the definition I used is that a team's ball movement is actually the spatial distribution of the ball's trajectory during its possessions. And now the question is how do you basically concretely describe this distribution by using ideally just one number. So the key idea that I used is to quantify the dimensionality of the trajectory, of the ball's trajectory during the possessions, and in order to do that I used the notion of fractal dimension. So fractal dimension, very briefly, is a single value that basically describes the complexity of a set of data points, and the benefit it has as compared to topological dimensionality is that it takes real values. So it's basically more fine-grained, and you can do easier comparisons. So what I did is that for every possession, I computed the fractal dimensionality of the ball trajectory, and then I tried to see how this correlates with the outcome of possession. Because in order to actually evaluate the ball movement, you would most probably need to do manual annotation of the possessions, which is obviously time-consuming. So I took an indirect approach for the evaluation. So I calculate the correlation between the fractal dimensionality of a ball trajectory during a possession and find the correlation basically with whether the possession resulted in a made field goal or a missed field goal or a turnover. And there was a strong and significant correlation between these two. And in particular, successful possessions tend to have lower fractal dimensionality as compared to possessions that end up with a miss or a turnover. And here are two representative examples of trajectories where the top trajectory was a made field goal which had a low fractal dimensionality, whereas the second trajectory was a missed field goal with a much higher fractal dimensionality. So the second outcome of good team chemistry is good collaboration, good connectivity between the players. This connectivity lends itself to methods from complex network theory. So why we use networks? One example I want to give about why networks are important is basically with these two objects. You have a pencil and you have a diamond, which, as we all know, they have completely different properties, they have completely different value, but they are both made of the same main ingredient, which is carbon. However, what is different is how the atoms of carbon are connected. And this structure of the carbon of atoms leads to a system which in total is more than the sum of its parts. In this case, obviously, is the diamond, and in the case of pencil, it's most probably less than its sum. So the same happens with teams, right? So you have individuals which are players, and the way they're connected, they might lead to a system that it's more than the sum of its parts. So what I did is that I used a passing network, where basically every node in the network is a player, and there is an edge from player I to player J if I has passed to J. And in order to quantify the connectivity in such network, one thing that you can do is that you can use the Laplacian matrix of the network and use the second smallest eigenvalue of this network, which I term as the team chemistry eigenvalue. So very briefly, the Laplacian of a network, the Laplacian matrix of a network is just the degree matrix minus the adjacency matrix, and the second smallest eigenvalue is called algebraic connectivity, and essentially the intuition is that the higher this value, the more connected, the better connected network is. So here's an example visualizing the network at the game between Charlotte and Sacramento, and we see that the Kings had a higher eigenvalue, and as you can see, it is overall better connected. So Charlotte's network is more connected, it has a sub-network that is better connected, but overall the connectivity of the Sacramento Kings, it's much better. So in order to evaluate how this might be capturing things like team chemistry, I calculated the difference in the team chemistry eigenvalue between two opposing teams, and I correlated with the point differential that they had. And what we saw is that there is a correlation, but obviously we cannot claim it's significant. We had only 5 games, but there seems to be a trend there. So in conclusion, complex systems is a good approach to model sports and intangibles. We can use other network metrics such as assortativity, modularity, community, and you can also use methods from statistical physics such as the cavity method to actually find players that are catalysts or inhibitors to the team chemistry in analogy to the actual chemistry. So, thank you.
All right, our next open division finalist, Tiffany Kelly.
Sorry, I have a Prezi, guys, so. Perfect. Good morning, everyone. Thanks for being here. My name is Tiffany Kelly. I currently work within statistics for LSU Athletics. And so my hack for this hackathon was the hustle difficulty complex. So as you all know, the difficulty complex with crediting and discrediting players, splitting apart points, created by Dean Oliver. I wanted to see this in relation to hustle. So similar to in finance, assigning a tangible value of dollar amounts to an intangible asset, I wanted to do the same thing for assigning points, which is our tangible value in basketball, to the intangible asset of hustle. So the three methodologies that I used: first, I had to grab the count data of all the 5 hustle stats. So these hustle stats were officially released by the NBA last year. So I first had to grab that count data, and I did that with having matrices of the XY coordinates of player and ball locations mapped to play-by-play results data that we got that would output the X and Y location of a hustle event. So with that X and Y location, I then used the distance formula, and once I grabbed that count data, I then inputted into the formulas that I created. So hustle part on the offensive end for points produced, and then hustle stops on the defensive end for points allowed. Okay, so delving a little bit deeper into kind of the count data and the definition between with the 5 hustle stats. So first, contested shots, that was pretty straightforward. That was a defender 0 to 3.5 feet away, and then charges drawn. So that play result was an offensive foul charge, and I measured the opponent distance for that. Screen assists, play result was a field goal made, and I measured the teammate distance. Loose balls are covered, and deflections are a little bit more difficult because these don't have play results. So loose balls are covered. I first measured the distance between the ball being 3 feet away, so it would be a loose ball. And I had to separate this for offensive and defensive. So offensive was a save of possession, and defensive was a change of possession. And deflections, the ball XY coordinates had to be equal to the opponent XY coordinates as he's deflecting the ball. So got that count data, and here's kind of an output that I had on my computer. So Taj Gibson drew a charge on Amari Stoudemire. So the players on the left-hand side would be the ones that get that count data for the charge drawn. And the ones on the right-hand side are the ones that are actually charging, fouling. All right, so some nasty formulas, but at the top is the original points produced formula, and everything in red, blue, and orange is kind of what I created and added in. So hustle part. All of the different colors are the hustle stats, and each are multiplied by the probability that it was a successful hustle event. So for screen assists and offensive loose balls recovered, they're multiplied by team play percentage, so basically from saving that possession, how more they're likely to score on that possession. So producing a point, and it's there in words as well, if math is too much. And then points allowed, this is a little bit more difficult. So we had stop percentage embedded into defensive ratings. And so I divided stops into hustle stops and then just defensive stops from like steals and blocks. So hustle stops, we had contested 2s and 3s multiplied by the success of that event, so a missed shot. And charges drawn, defensive loose balls recovered, multiplied by the failure that the opponents got the ball back and couldn't score on that possession. And the deflections multiplied by forced turnovers, because that's essentially what we want. We're stopping that play from happening. So results. This was honestly the only picture of LeBron I could find, kind of biased. But so this is the net change between points produced and points allowed from the original formula and the new formula that I had. And naturally, there are more hustle stats on the defensive end, so players that hustle more defensively are going to have a greater change in points, because there are only, I think, 4 hustle stats on the defensive and 2 on offensive. So, thank you.
Okay, and our final open division finalist, Devin Plore.
we go. Hey guys, my name is Devin Pluler. I manage the analytics department at Toronto FC, and today what I've got for you is the posterize effect. So I've kind of found that in my experience so far working for a club, I've found that there's a, in the applied sports analytics theater, there's kind of an unexpected trade-off between a model's sophistication and a model's usefulness. While something more sophisticated, maybe more predictive, a simpler model is often easier to explain and implement, especially when we're talking to coaches and decision makers. What I've created during the hackathon by combining tracking and play-by-play data is a proxy for players' mental toughness while keeping the metric fairly intuitive and understandable. So when a player gets scored on, how do they react? Do they sulk themselves back up the court, or do they get pumped up? What is their body language after that? So what I've got is a measurement for how quickly players get back up on offense after a team concedes a field goal. And what I found that was actually kind of unexpected here is that defenders run faster than their teammates after being scored on by about half a second. I kind of expected the opposite here. I kind of expected players to sulk. What was kind of unexpected, though, is I realized when I split this a little bit differently and I looked at how close that player was defending. So by breaking down near defenders from far defenders, I put a threshold here at 5 feet. So once you kind of break that apart, defenders who were very close to the score tended to sulk back up the court, whereas were those players kind of posterized. Now, what's interesting is that obviously not all players behave this way, right? Different players respond to adversity in different ways. I'm just thinking about the Celtics game the other night against the Cavs when Rozier threw the ball at I think LeBron after a dunk, right? So for the players that we evaluated, 21 of the players did indeed move faster after conceding a shot, where 14 of them, were slower. Now, if I was a coach, I'd want to know who those players are. I think that would be a piece of interesting information, a piece of additional context in terms of making a player decision or something like that. Now, obviously, there are some limitations to this approach here. Obviously there's some per position effects, right, that I haven't really accounted for. Obviously the center's got to travel a little bit further up the court or something like that. And especially things like point guards, right, how they're going to behave after conceding a shot or their team conceding a shot is going to be a lot different than, other players or positions on the field. Also things like game state, right? How does a team behave when they're winning versus they're losing? The rate, the speed of game, I'm sure changes quite a bit. Are they a bit lazier when they're up by a lot of points? Are they depressed when they're down by a lot? Things like that. But with a few more hours of hacking through the data, maybe we can do a little bit more. Thank you.
All right, thank you everybody for attending. This was the first time we've been able to have these presentations during the conference itself, and we appreciate the opportunity to share this work. They had 6 hours to work on that data, and they came up with some really interesting things. Please join us at the Alpha Awards to see who triumphs. Thank you.